Tonight, we are going to tell the story of something so close, so familiar, so constant in our lives that most people have stopped wondering about it. It hangs in the sky almost every night. It has been worshipped, feared, mapped, and walked upon. Poets have written about it for thousands of years. Astronauts have left footprints on its surface that will last for millions. And yet, despite all of that, despite the fact that it is the nearest world to Earth, the only celestial body a human being has ever touched, we are still discovering things about it that no one expected. We are talking about the moon. You think you know the moon. You have seen it your whole life, a pale disk in the night sky, cycling through its phases, full and bright one week, a thin crescent the next, vanishing entirely before returning again. It seems simple, it seems understood. It seems like the most boring object in the solar system compared to the volcanoes of Io, the oceans of Europa, the methane lakes of Titan. But here is what most people do not know. The moon is not what it appears to be. It was born in the most violent event in Earth's history, a collision so catastrophic that it melted the entire surface of our planet into a sea of magma thousands of kilometers deep. Its interior is not dead. It still shakes with moonquakes that can last over 10 minutes, and scientists do not fully understand why. It once had a magnetic field as strong as Earth's, and then it vanished, and we are still debating when and how. Beneath the eternal shadows of its South Pole craters, places where sunlight has not reached for billions of years, there are over 600 billion kilograms of water ice, enough to fill 250,000 Olympic swimming pools. And buried deep inside Earth's own mantle, 2 continent-sized blobs of alien rock, remnants of the world that crashed into Earth to create the moon, are still sitting there 4.5 billion years later, like a scar from the most ancient wound in our planet's history. Tonight, we are going to walk through 7 surprising discoveries about the moon. Discoveries that have changed how we think about our nearest neighbor, about the history of Earth, and about the future of human exploration. By the end of tonight, you are going to understand why the moon is not the quiet, dead world you were taught about in school, and why the next chapter of its story is just beginning. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. The moon's story begins 4.5 billion years ago, in a solar system that looked nothing like the one we know today. This is surprising discovery number 1. The moon was born in violence, and the evidence is still buried inside our planet. The early solar system was a dangerous place. The planets had not yet settled into their current stable orbits. The inner solar system was crowded with dozens of protoplanets, rocky worlds ranging in size from the dwarf planet series to something as large as Mars, all jostling for position, their orbits crossing and recrossing, collisions frequent and catastrophic. It was a demolition derby on a planetary scale, and the prize for surviving was a stable orbit around the Sun. Earth, about 4.5 billion years ago, was one of these protoplanets. Already large, already molten, already accumulating mass from the debris of the solar nebula. It was not alone. Sharing a similar orbital neighborhood was another protoplanet, smaller than Earth, roughly the size of Mars, with its own iron core, its own mantle, its own history. Scientists have given this world a name, Theia, after the Greek Titaness who was the mother of Selene, the goddess of the moon. Theia and Earth were on a collision course. The details of the impact are still debated. whether it was a head-on collision or a glancing blow, whether Theia was moving fast or slow, whether the two worlds had similar compositions or different ones. But the broad outlines are now well established, supported by decades of computer simulations, laboratory analysis of lunar rocks, and the laws of physics. Roughly 4.5 billion years ago, Theia struck the Earth. The energy released was beyond anything we can meaningfully comprehend. The impact vaporized a significant portion of both worlds. The surface of the Earth was melted to a depth of hundreds of kilometers, creating a global magma ocean, a sea of molten rock covering the entire planet, glowing white-hot, with surface temperatures exceeding several thousand degrees. The force of the collision blasted an enormous plume of vaporized rock and debris into orbit around the Earth. A disk of superheated material, thousands of degrees hot, orbiting the ruined planet like a ring of fire. From this disk, over a period of perhaps a few hundred years, an eye blink in geological time, the moon coalesced. Gravity pulled the orbiting debris together, particle by particle, fragment by fragment, until a new world had formed. A world born not from the slow accretion of the solar nebula like the planets, but from the wreckage of a catastrophic impact. The moon was born in fire, assembled from the shattered remains of two worlds. For decades, this was the leading hypothesis for the moon's formation, the giant impact hypothesis, first proposed in a modern form in the mid-1970s. It explains several puzzling features of the moon. Why does the moon have a much smaller iron core than expected? Because most of Theia's iron core merged with Earth's core during the impact, leaving the debris disk and the moon that formed from it depleted in iron. Why are the moon's rocks chemically similar to Earth's mantle? Because the debris disk was largely composed of Earth's mantle material, blasted into orbit by the impact. Why does the moon have almost no volatile elements, no water, no nitrogen, no carbon compounds? Because the extreme heat of the impact vaporized the volatiles, which escaped into space before the moon could form. The giant impact hypothesis has other strengths as well. It explains why the Earth-Moon system has an unusually high angular momentum. The total rotational energy of the system, combining Earth's spin and the Moon's orbital motion, is higher than you would expect for a planet of Earth's size. A giant impact would have imparted an enormous amount of rotational energy to the system, spinning up the young Earth and flinging debris into a fast-orbiting disk. It also explains the Moon's relatively low density compared to Earth, about 3.3 grams per cubic centimeter, versus Earth's 5.5. The Moon is made mostly of silicate rock with a small iron core, exactly what you would expect if it formed primarily from the mantle material of two colliding worlds, after most of the dense iron had already sunk to their cores. The hypothesis has been refined and debated over the decades. Some models propose a relatively slow, grazing collision. Others propose a nearly head-on impact at high velocity. A 2012 study by Robin Chang'e at the Southwest Research Institute in Colorado showed that a high-energy, high-spin impact could produce a moon with the right composition, while also explaining the remarkable chemical similarity between Earth and Moon rocks. A similarity so close that it initially puzzled scientists because a Mars-sized impactor should have had a different isotopic composition than the proto-Earth. Chang'e's model showed that under certain impact conditions, the material from both bodies could be thoroughly mixed in the debris disk, erasing the original compositional differences and producing a moon that is chemically nearly identical to Earth's mantle. A 2024 study published in science added another piece to the puzzle, analyzing the isotopic composition of elements like titanium and oxygen in both Earth rocks and lunar samples, and concluding that Theia most likely originated from the inner solar system, the same region as Earth, rather than from the outer solar system. This would naturally explain the chemical similarity. Theia and Earth were made from the same raw materials, formed in the same neighborhood, and had similar compositions before they collided. The giant impact hypothesis was elegant, powerful, and well supported by evidence. But in 2023, the story became even more remarkable. A team of researchers led by Chandrayaan at the California Institute of Technology published a study in the journal Nature that sent shockwaves through the planetary science community. They had found Theia, or rather, what was left of it, and it was not in space. It was inside the Earth, deep within Earth's mantle. Seismologists have long known about two enormous, mysterious structures, continent-sized blobs of unusually dense material sitting at the boundary between the mantle and the core, roughly 2,900 kilometers below the surface. These structures are called Large Low-Velocity Provinces, or LLVPs, because seismic waves, the vibrations from earthquakes that travel through the Earth's interiors, slow down dramatically when they pass through them. One LLVP sits beneath Africa, the other sits beneath the Pacific Ocean. Each one is roughly twice the size of the Moon. Together, they represent about 3% of Earth's total mass, roughly the mass of the Moon itself. For decades, no one knew what these structures were. They were clearly different from the surrounding mantle, denser, chemically distinct, possibly iron-rich. Some scientists proposed that they were remnants of ancient subducted oceanic crust that had sunk to the bottom of the mantle. Others suggested they were primordial material from the Earth's original formation that had never been fully mixed. Yuan and his colleagues proposed something far more dramatic. The LLVPs are the remains of Theia. When Theia struck the Earth 4.5 billion years ago, most of its mantle was blasted into orbit to form the Moon. But a significant fraction of Theia's iron-rich material sank deep into Earth's molten interior, settling at the core mantle boundary, where it has remained ever since. The simulations showed that the energy of the impact was concentrated in the upper mantle, leaving the lower mantle cool enough for the dense iron-rich Theia material to sink intact rather than mixing throughout the Earth. The evidence was compelling. The density of the LLVPs matched what you would expect from Theia's iron-enriched mantle material. The location, sitting on the core mantle boundary, was exactly where dense material would settle after a giant impact. And the total mass of the two LLVPs was consistent with the fraction of Theia that simulations predicted would be retained by Earth rather than ejected into the debris disk. If Yuan's team is right, and the evidence continues to mount, then the Moon's birth left a scar not just in space, but inside our own planet. The two largest structures in Earth's deep interior are alien, remnants of a dead world that crashed into ours 4.5 billion years ago and never left. Every time a seismic wave from an earthquake passes through one of those blobs, it is passing through a piece of Theia, the planet that died so that the Moon could be born. The age of the Moon itself has been refined by studying the rocks that Apollo astronauts brought back from the lunar surface. In 2023, a team led by Philip Heck at the Field Museum in Chicago analyzed tiny zircon crystals found in lunar dust samples collected during the Apollo 17 mission in 1972. Zircon is an extraordinarily durable mineral, nearly indestructible, resistant to heat and pressure, capable of surviving billions of years without significant alteration. And zircon contains trace amounts of uranium, which decays into lead at a known rate, providing a precise radioactive clock. The zircon crystals from Apollo 17 told a clear story. They had formed 4.46 billion years ago, making the moon about 40 million years older than previous estimates had suggested. The moon is not 4.42 billion years old, as earlier dating had indicated. It is 4.46 billion years old, formed just about 100 million years after the birth of the solar system itself. The collision between Earth and Theia happened very early in the solar system's history, when the inner solar system was still a chaotic, violent place. And the moon that emerged from that collision was nothing like the cold, quiet world we see today. It was a hellscape. This is surprising discovery number 2. The moon was once covered in a global ocean of molten rock, a magma ocean that took hundreds of millions of years to cool. When the moon first formed from the debris disk orbiting Earth, it was entirely molten. The energy of the impact and the gravitational compression of the coalescing material heated the young moon to temperatures of over 1,000 degrees Celsius. The entire surface and much of the interior was a vast ocean of liquid rock, glowing orange and red against the black sky, with no solid surface anywhere. If you could have orbited the young moon in those first days, you would have seen a world that looked less like the moon and more like a drop of lava suspended in space, a sphere of incandescent rock radiating heat into the void, its surface churning and roiling as convection currents brought fresh magma up from below and cooled material sank back down. The sky above the magma ocean was not empty. The extreme heat vaporized volatile elements from the surface, creating a tenuous atmosphere of sodium, potassium, and silicon monoxide, a ghostly shroud of rock vapor hanging above a sea of liquid rock. As the surface cooled, this atmosphere would have condensed and rained back down. Not water rain, but rock rain, droplets of molten mineral falling from a sky of vaporized stone onto an ocean of lava. It is a scene so alien, so far removed from anything in human experience, that it belongs more to science fiction than to the history of the world we see hanging peacefully in our night sky. This global magma ocean is not speculation, it is one of the most well-established facts about the moon's early history, supported by the chemistry of the lunar rocks themselves. As the magma ocean cooled, different minerals crystallized at different temperatures and different depths. Dense minerals like olivine and pyroxene, rich in iron and magnesium, sank to the bottom. But one mineral, plagioclase feldspar, rich in calcium and aluminum, was less dense than the surrounding magma. It floated to the top, forming a solid crust of a rock type called anorthosite, a pale, light-colored rock that makes up the ancient lunar highlands, the bright, heavily cratered regions that you can see with the naked eye when you look at the full moon. The lunar highlands are the oldest parts of the moon's surface, the original crust formed from a floating layer of crystallized feldspar on top of a cooling magma ocean. They are roughly 4.4 billion years old, and they bear the scars of every impact that has struck the moon since they formed. The dark regions, the lunar maria, from the Latin word for seas, because early astronomers thought they might be oceans, are younger, formed by volcanic eruptions that flooded large impact basins with dark basalt lava between about 3.9 and 3 billion years ago. The magma ocean took a remarkably long time to cool. Recent models suggest that the process lasted anywhere from tens of millions to perhaps 200 million years, a period during which the moon transitioned from a fully molten world to a world with a solid crust, a partially molten interior, and a gradual cooling that continues to this day. The cooling was not smooth or uniform. As the magma ocean solidified, it released heat unevenly, creating convection currents that stirred the remaining liquid, redistributed chemical elements, and set the stage for the volcanic activity that would later flood the Maria. In 2012, researchers at the University of Cambridge proposed a modification to the magma ocean model, suggesting that the ocean was not a simple liquid layer, but a slushy mixture of crystals and liquid, more like a thick, churning slurry than a clear pool of molten rock. This slushy model better explains the composition and thickness of the anorthosite crust and resolves some long-standing problems with the classic magma ocean theory. The moon's crust was not a simple raft of floating crystals. It was a complex, evolving structure that grew from a roiling, semi-solid slurry of magma and minerals. The magma ocean hypothesis is one of the great triumphs of lunar science, a theory that emerged directly from the analysis of Apollo samples and that has been refined, tested, and confirmed over 5 decades of research. It tells us that the moon we see tonight, the pale, quiet, apparently dead world hanging in the sky, was once a seething ball of liquid rock, as hot and violent as any world in the solar system. The calm surface we see is a mask hiding a violent past. This is surprising discovery number 3. The moon is not dead. It still shakes, and we do not fully understand why. When the Apollo astronauts walked on the moon between 1969 and 1972, they did more than collect rocks and plant flags. They deployed a network of scientific instruments on the lunar surface, instruments that continue to operate long after the astronauts return to Earth. Among the most important were the seismometers, sensitive devices designed to detect vibrations in the lunar surface, the same way seismometers on Earth detect earthquakes. The first seismometer was deployed on July 21, 1969, by Neil Armstrong and Buzz Aldrin during Apollo 11. It was a relatively simple instrument, powered by solar cells designed to operate for only about 3 weeks, but it detected its first moonquake within days, before the astronauts had even left lunar orbit. Subsequent Apollo missions, 12, 14, 15, and 16, deployed more advanced seismometers as part of the Apollo Lunar Surface Experiments Package, or LSIP. These instruments were nuclear-powered, using small radioisotope thermoelectric generators that could operate independently for years. By the time the full network was in place, 4 seismometers were operating simultaneously at different locations on the near side, forming a sparse but functional seismic network. The Apollo seismometers operated from 1969 to 1977, 8 years of continuous monitoring, recording every vibration, every tremor, every impact on the lunar surface. Over those 8 years, they recorded nearly 12,000 seismic events, a rich data set that has been analyzed and reanalyzed for decades, yielding new insights with each generation of scientific tools. What they found surprised everyone. The moon is not seismically dead. It shakes, it trembles, it quakes, not as frequently or as violently as the Earth, but far more than anyone expected from a world with no plate tectonics, no active volcanoes, and no liquid water. The Apollo seismometers detected 4 distinct types of moonquakes. The first type, and the most common, are deep moonquakes. These occur at depths of roughly 700 kilometers below the surface, deep within the moon's mantle. They are caused by tidal forces, the gravitational pull of the Earth stretching and squeezing the moon's interior as the moon orbits in its slightly elliptical path. Just as the moon's gravity raises tides in Earth's oceans, Earth's gravity raises tides in the moon's rocky interior, flexing the deep mantle and triggering small but measurable seismic events. Deep moonquakes are generally mild, too faint to be felt by a person standing on the surface, but they are remarkably regular, occurring in predictable patterns tied to the moon's orbital period. The Apollo seismometers recorded thousands of them over 8 years. The second type are shallow moonquakes, and these are the ones that worry scientists. Shallow moonquakes originate at depths of about 20 to 30 kilometers below the surface, in the moon's upper mantle or lower crust. They are caused by the gradual cooling and thermal contraction of the moon's interior, the slow, inexorable shrinking of a world that is still losing heat from its formation 4.5 billion years ago. Unlike deep moonquakes, shallow moonquakes can be powerful, reaching magnitudes of up to 5.5 on the Richter scale, comparable to a moderate earthquake on Earth. And unlike earthquakes, which typically last seconds to a minute or two, shallow moonquakes can last over 10 minutes. The moon rings like a bell. This is because of the moon's structure. On Earth, earthquakes are quickly dampened by the presence of water, sediment, and the complex layered structure of the crust. The energy dissipates rapidly, absorbed by ocean water, scattered by soft sediments, attenuated by the plastic flow of warm rock in the lower crust. An earthquake of magnitude 5 on Earth might shake the ground for 30 seconds. On the moon, a comparable event shakes the ground for 10 minutes or more. The reason is that the moon has no water, no sediment, no soft layers to absorb the vibrations. Its crust is dry, rigid, and fractured by billions of years of impacts. The outer layer of the moon, the megaregolith, is a zone of heavily fractured rock, shattered by eons of bombardment, extending perhaps 20 kilometers deep. This fractured zone is excellent at scattering seismic waves, but terrible at absorbing them. When a moonquake strikes, the seismic waves bounce back and forth through this rigid, fractured medium, reverberating for minutes on end like the ringing of a gong. The Apollo 12 astronauts demonstrated this dramatically. After they had completed their moonwalk and returned to the lunar module, they deliberately crashed the ascent stage of the Apollo 12 lunar module onto the moon's surface. The impact was equivalent to about a ton of TNT. The seismometers, located about 72 kilometers from the impact site, recorded the resulting vibrations for nearly an hour. The signal built slowly, peaked, and then faded with agonizing slowness, dying away over 55 minutes. The moon literally rang like a bell. The result was so startling that the scientists at first thought their instruments were malfunctioning. No one had expected the seismic signal to persist for so long. On Earth, a comparable impact would have produced a sharp shock wave that faded in seconds. On the moon, the same energy reverberated through the dry, fractured crust for almost an hour, bouncing back and forth, slowly dissipating through internal friction in a medium that had almost no capacity to absorb it. NASA repeated the experiment with even more dramatic results during Apollo 13, Apollo 14, Apollo 15, and Apollo 16, deliberately crashing spent Saturn V third stages, each one weighing about 14 metric tons, into the moon at speeds of about 2.5 kilometers per second. The impacts were enormous, equivalent to roughly 11 tons of TNT each, and the seismic signals lasted for up to 4 hours. The moon did not just ring, it reverberated, resonated, and vibrated like a world-sized tuning fork. The third type are impact moonquakes, caused by meteoroids striking the lunar surface. Without an atmosphere to burn up incoming debris, the moon is constantly bombarded by small rocks and dust particles from space. Each impact creates a small seismic event that the Apollo seismometers could detect. The fourth type are thermal moonquakes, tiny, extremely shallow tremors caused by the extreme temperature swings between lunar day and lunar night. During the lunar day, which lasts about 2 weeks, surface temperatures can reach over 120 degrees Celsius. During the lunar night, also about 2 weeks long, temperatures plunge to minus 170 degrees Celsius or lower. This roughly 300-degree temperature swing causes the surface rocks to expand and contract, cracking and popping with each cycle. The thermal moonquakes are small, more like the creaking of a house than an earthquake, but they are constant and ubiquitous. But here is the mystery. The shallow moonquakes, the powerful, prolonged ones, do not fit neatly into any simple model. The moon should be cooling uniformly, contracting slowly and predictably. But the shallow moonquakes occur in specific locations, at unpredictable intervals, with varying magnitudes. Some scientists believe they are associated with ancient fault lines, fractures in the crust created by the cooling and shrinking of the moon's interior. Others have suggested that they may be related to the moon's internal structure in ways we do not yet understand. The Apollo seismic network was small, just 4 stations, clustered on the near side, and it provided only a partial picture. We need more seismometers, in more locations, on both sides of the moon, to fully understand what is happening inside our nearest neighbor. The moon's interior itself has been revealed in broad strokes by the Apollo seismic data. Seismologists use the travel times of seismic waves, both the primary waves, which are compression waves that travel through solids and liquids, and the secondary waves, which are shear waves that travel only through solids, to map the moon's internal layers, the same way doctors use ultrasound to image the inside of a body. When a seismic wave hits a boundary between layers of different density or composition, it changes speed and direction. And by measuring those changes at multiple stations, scientists can build a picture of what lies beneath. The picture that emerged was both familiar and alien. At the center is a small iron core, much smaller than Earth's core relative to the size of the body, only about 350 kilometers in radius compared to Earth's core radius of roughly 3,500 kilometers. The moon's core is less than 1% of its total mass compared to about 32% for Earth. Surrounding the core is a partially molten layer, a zone of partially liquid rock, perhaps 200 kilometers thick, that may still be fluid enough to sustain some degree of flow. Then comes the thick mantle of silicate rock extending to within about 60 kilometers of the surface, and finally the crust, thinner on the near side, thicker on the far side, ranging from about 30 to more than 60 kilometers in depth. The discovery of the partially molten layer surrounding the core was crucial for understanding the moon's thermal history. It means the moon's deep interior is still warm enough to maintain some liquid, not fully molten, but not fully solidified either. The moon is still cooling, still losing the heat from its formation 4.5 billion years ago, still slowly freezing from the outside in. It is a world in transition between a hot past and a cold future, and we are witnessing one moment in that long, slow transformation. The asymmetry between the near side and the far side is one of the moon's great puzzles. The near side, the face that always points toward Earth, has a thinner crust and is dominated by the dark volcanic Maria, the ancient lava flows that filled large impact basins. The far side has a much thicker crust and almost no maria. It is dominated by the bright, ancient, heavily cratered highlands. Why the two hemispheres are so different is still debated. One leading theory suggests that the distribution of radioactive elements, which produce heat as they decay, was concentrated on the near side, thinning the crust and enabling volcanic eruptions there, while leaving the far side geologically quieter. Another theory involves the geometry of the giant impact itself, which may have distributed heat and material asymmetrically. This is surprising discovery number 4. The moon once had a powerful magnetic field, and then it disappeared. Today, the moon has no global magnetic field. If you stood on the lunar surface with a compass, the needle would spin aimlessly. There is no magnetic north, no magnetic south, no field to align with. The moon is magnetically dead. But it was not always this way. When scientists analyzed the rocks brought back by the Apollo missions, they found something unexpected. Many of the oldest lunar rocks were magnetized. They contained tiny grains of iron and iron-bearing minerals that were aligned in a specific direction, frozen in place when the rock cooled and solidified, preserving a record of the magnetic field that existed at the time. The rocks were telling a story. The moon once had a magnetic field, and it was strong. How strong? At its peak, roughly 4 billion years ago, the lunar magnetic field may have been comparable to Earth's, perhaps even stronger in some estimates. That is a remarkable claim, because magnetic fields in rocky bodies are generated by the dynamo effect, the churning of liquid metal in a planet's core, which converts kinetic energy into magnetic energy. Earth's magnetic field is generated by the convection of liquid iron in its outer core. For the moon to have had a similar field, it must have had a liquid convecting core, a core that was hot enough and active enough to sustain a dynamo for hundreds of millions, perhaps billions, of years. The evidence from Apollo samples tells a dramatic story. The magnetic field was strong about 4 billion years ago, during the period when the moon's interior was still hot from formation. Then it appears to have weakened, possibly fluctuated, and ultimately died. Research published by MIT scientists in 2019 pinned down the timing. The lunar dynamo shut off approximately 1 billion years ago. For roughly 3.5 billion years, the moon had a magnetic field, generated by a churning liquid core, shielding the surface from the solar wind, creating a magnetic bubble around the world, much like Earth's magnetosphere does today. And then it stopped. The core cooled. The convection ceased. The dynamo died. The magnetic field faded away, leaving the moon exposed and naked to the solar wind, the constant stream of charged particles flowing from the sun. Without a magnetic shield, the solar wind strips atoms from the lunar surface, implanting hydrogen and helium into the uppermost layer of soil, and bombarding the surface with radiation. The Chang'e Site mission, China's extraordinary achievement in 2024, which collected and returned 1,935 grams of samples from the far side of the moon, the first samples ever returned from the lunar far side, has added a new chapter to this story. Analysis published in Nature in 2025 provided the first paleomagnetic data from the far side of the moon and revealed something unexpected. The magnetic field may have rebounded around 2.8 billion years ago, strengthening temporarily before its final decline. The far side magnetic data suggests that the lunar dynamo did not simply fade away. It fluctuated, surging and weakening over billions of years before finally dying out. What caused these fluctuations? The answer may lie in the moon's tidal interaction with Earth. As the moon orbited closer to Earth in its early history, and it was much closer, as we will discuss later, the tidal forces were stronger, generating more internal heat, potentially driving convection in the core and sustaining the dynamo. As the moon slowly spiraled outward and the tidal heating diminished, the core gradually cooled, the dynamo weakened, and the magnetic field died. The fluctuations may represent episodes when tidal heating temporarily reinvigorated the core, like blowing on dying embers. The loss of the magnetic field had profound consequences. With the magnetosphere gone, the solar wind began directly bombarding the lunar surface, gradually stripping away whatever tenuous atmosphere the moon may have had, implanting solar wind particles into the soil and transforming the uppermost layer of the surface into a strange, glassy, radiation-processed material called the regolith. The moon's surface today is not bare rock. It is covered in a layer of fine, powdery regolith, typically several meters deep on the Maria and potentially tens of meters deep on the ancient highlands, created by billions of years of meteoroid impacts and solar wind bombardment. The regolith is one of the most processed materials in the solar system, ground to powder by impacts, irradiated by cosmic rays, chemically altered by the solar wind, and completely unlike any soil on Earth. The Apollo astronauts learned this firsthand, in ways that no laboratory analysis could have predicted. Lunar dust is extraordinarily fine. Most particles are smaller than 30 micrometers, roughly the diameter of a human hair, and extraordinarily abrasive. On Earth, wind and water erode the sharp edges of sand grains, rounding them over time. On the moon, there is no wind and no water. The grains are never rounded. They remain jagged, angular, freshly fractured. Tiny shards of glass and mineral with razor-sharp edges that cling to everything they touch. The dust clung to the astronauts' spacesuits with a ferocity that surprised everyone. It worked its way into the woven fabric of the suit layers, abraded the visors of their helmets, and jammed the mechanisms of their equipment. Chandrayaan, the commander of Apollo 17 and the last human to walk on the moon, later described the dust as one of the most significant challenges of lunar exploration. The fine particles clung to every surface by a combination of electrostatic charge built up by the constant bombardment of ultraviolet radiation and solar wind particles, and mechanical interlocking, the jagged grains hooking into the fibers of the suits like microscopic burrs. When the astronauts returned to the lunar module and removed their helmets, they could smell the dust, a sharp, burnt, metallic smell, like gunpowder or spent fireworks. Harrison Schmitt, the geologist astronaut on Apollo 17, experienced what he called lunar high fever, nasal congestion and irritation from breathing the fine particles that had been tracked into the cabin. The dust was not just a nuisance, it was a potential health hazard. Some scientists have compared the biological effects of lunar dust to those of silicosis, the lung disease caused by inhaling fine quartz dust in mines and quarries on Earth. The jagged, glass-rich particles could lodge in the lungs, resist the body's attempts to clear them, and potentially cause chronic inflammation and tissue damage. Solving the lunar dust problem, keeping it out of habitats, off of spacesuits, away from sensitive equipment, and out of astronauts' lungs, is one of the major engineering challenges facing any attempt to establish a permanent human presence on the moon. Several approaches are being studied, including electrostatic dust removal systems that use electric fields to repel charged particles, specialized coatings that prevent dust adhesion, and airlock designs that use magnetic or electrostatic curtains to strip dust from suits before astronauts enter the habitat. The dust is not just an inconvenience, it is one of the moon's most formidable defenses against long-term human occupation. This is surprising discovery number 5. The moon is hiding water, vast quantities of it, in places where sunlight has never reached. For most of the history of lunar science, the moon was considered bone dry. The Apollo samples contained no water. The moon has no atmosphere, no rain, no rivers, no oceans, no ice caps visible from orbit. The surface temperature swings between blistering heat and extreme cold, and the lack of atmospheric pressure means that liquid water cannot exist on the surface. It would either boil away instantly or sublimate from ice directly into vapor. The moon was dry. Everyone knew it. It was one of the basic facts about our nearest neighbor, as established and unquestioned as the fact that it has no air. And then everything changed. The conviction that the moon was dry was so strong that when traces of water were found in some Apollo samples in the 1970s, scientists dismissed them as terrestrial contamination, moisture from Earth's atmosphere that had crept into the sample containers. It seemed impossible that water could survive on the moon. The temperatures were too extreme, the vacuum was too harsh, the radiation was too intense. Water on the moon was not just unlikely, it was, in the scientific consensus of the time, essentially impossible. The first hint came in 1994, when the Clementine spacecraft, a joint mission between NASA and the Strategic Defense Initiative, detected anomalous radar returns from the moon's south pole that were consistent with the presence of water ice. The result was intriguing but inconclusive. The radar signature could have been caused by rough, blocky terrain rather than ice. 4 years later, in 1998, the Lunar Prospector Orbiter detected elevated levels of hydrogen at both poles, consistent with water ice, but not proof. The breakthrough came in 2008 and 2009, in a remarkable 1-2 punch of discovery that overturned decades of established science and transformed our understanding of the moon's potential as a destination for human exploration. In 2008, India's Chandrayaan spacecraft, the country's first lunar mission, and one of the most ambitious debut planetary missions in the history of space exploration, carried an instrument called the Moon Mineralogy Mapper, or M3, built by NASA's Jet Propulsion Laboratory, which detected the spectral signature of water molecules and hydroxyl groups on the lunar surface. The detection was not limited to the poles. It found evidence of water across the sunlit surface of the moon, bound into the soil at extremely low concentrations. The moon was not dry. It had water, not much, far less than the driest desert on Earth, but real, measurable, undeniable. Then, in 2009, NASA delivered the exclamation point. The El-Cross mission, the Lunar Crater Observation and Sensing Satellite, deliberately crashed a spent rocket stage into a permanently shadowed crater near the moon's south pole, at a crater called Cabeus. A trailing spacecraft flew through the debris plume, analyzing its composition with spectrometers and cameras before it too crashed into the surface. The result, 155 kilograms of water detected in the plume, water ice sitting in the permanent shadows of a polar crater preserved for billions of years by the extreme cold. The results confirmed what many had hoped and few had dared to predict. The moon had water locked in its polar shadows, delivered over billions of years by comets and asteroids, and preserved by the merciless cold. The moon's poles are unique environments in the solar system, perhaps the most extreme cold traps accessible to human exploration. Because the moon's rotational axis is tilted only about 1.5 degrees relative to the ecliptic, compared to Earth's 23.5-degree tilt, the Sun never rises more than a few degrees above the horizon at the poles. The floors of deep craters near the poles are permanently shadowed. They have not seen sunlight for billions of years. Temperatures in these permanently shadowed regions drop to about minus 250 degrees Celsius, colder than the surface of Pluto, among the coldest temperatures measured anywhere in the solar system. At these temperatures, water ice is stable for billions of years, even in the vacuum of space. Any water that found its way into these cold traps, delivered by comets, asteroids, or created by chemical reactions between solar wind hydrogen and oxygen in the lunar soil, would be trapped indefinitely, accumulating over billions of years into deposits that could be enormous. And the estimates are staggering. Orbital measurements suggest that the Moon's permanently shadowed regions contain over 600 billion kilograms of water ice, enough to fill at least 240,000 Olympic swimming pools. And this may be a conservative estimate. Research published in 2020 identified thousands of smaller cold traps, shadowed areas as small as a few centimeters across, scattered across the polar regions, that could increase the total by 10 to 20%. In 2006, India's Chandrayaan 2 orbiter added another piece to the puzzle, publishing results from its dual-frequency synthetic aperture radar that detected subsurface ice in doubly shadowed craters, craters within craters, where the shadowing is so complete that ice may exist not just on the surface, but buried beneath a layer of regolith, protected from the slow erosion of sublimation by a blanket of dry soil. The water on the Moon is not just a scientific curiosity. It is a resource, potentially the most valuable resource on the Moon for future human exploration. Water can be split into hydrogen and oxygen by electrolysis. Oxygen is breathable. Hydrogen and oxygen together make rocket fuel. A permanent lunar base with access to water ice would not need to transport all of its water, air, and fuel from Earth. It could produce them locally, from the ice hiding in the eternal shadows. This is the concept of in situ resource utilization, using local materials instead of importing everything from Earth, and it is one of the key enabling technologies for sustained human presence on the Moon. This is why every major space agency in the world is focused on the lunar South Pole. It is where the water is, and water on the Moon is not just a scientific curiosity or a convenient resource. It is the key that could unlock the rest of the solar system. A lunar base with access to water ice is not just a research outpost. It is a fueling station, a place where spacecraft can be refueled with hydrogen and oxygen produced from local resources, dramatically reducing the cost and complexity of missions to Mars and beyond. This is surprising discovery number 6. The Moon is slowly leaving us, and the evidence is measured in centimeters. The Moon is not staying put. It is moving away from the Earth, slowly, imperceptibly, but measurably. Every year, the Moon recedes from the Earth by about 3.8 centimeters, roughly the rate at which your fingernails grow. It is an absurdly small distance by human standards, but over geological time, it adds up to an enormous change. We know this because of one of the most elegant experiments in the history of science. An experiment that has been running continuously for over half a century and shows no signs of stopping. During the Apollo 11, 14, and 15 missions, astronauts placed retroreflector arrays on the lunar surface, small panels covered with corner cube prisms designed to reflect laser light directly back toward its source. The Apollo 11 reflector, deployed by Buzz Aldrin, is a square panel about 46 centimeters across, containing 100 fused silica corner cube prisms, each one a precision ground piece of glass shaped so that any light entering the prisms is reflected back exactly parallel to the incoming beam, regardless of the angle of incidence. The Apollo 14 reflector is identical in design. The Apollo 15 reflector is larger, containing 300 prisms, and provides a stronger return signal. The principle is simple. An observatory on Earth fires a short, intense pulse of laser light, typically a pulse lasting about 100 trillionths of a second, containing roughly 300 quadrillion photons, aimed at one of the reflectors on the Moon. The light travels to the Moon in about 1.3 seconds, hits the reflector, and bounces back. The observatory records the time of flight, the interval between sending the pulse and detecting the return photons, with atomic clock precision. Since light travels at a known constant speed, the time of flight gives the distance to the Moon with extraordinary accuracy. The numbers are humbling. Of the 300 quadrillion photons fired toward the Moon, only about 1 in 30 million actually hits the reflector. The rest miss, scattered by atmospheric turbulence, diffracted by the beam's natural spreading over the vast distance. Of the photons that hit the reflector, only a fraction are reflected back toward the observatory. And of those reflected photons, the return beam spreads over an area of about 20 kilometers on Earth's surface by the time it arrives, so only a tiny fraction enter the telescope. On a good night, the observatory detects about 1 returned photon per pulse. 1 single photon out of 300 quadrillion, surviving the round trip of 770,000 kilometers, and carrying with it a measurement accurate to about 1 millimeter. The primary observatory for this work has been the McDonald Observatory in the Davis Mountains of West Texas, which began lunar laser ranging in 1969, just weeks after the Apollo 11 reflectors were deployed, and has continued almost without interruption ever since. The Apollo project, the Apache Point Observatory lunar laser ranging operation in New Mexico, has pushed the precision even further, using a 3.5-meter telescope and advanced photon detection to achieve millimeter-level accuracy. Observatories in France, Italy, Germany, and Australia have also contributed, building a global dataset spanning more than 50 years of continuous measurements. The Soviet Union's Lunokhod 1 and Lunokhod 2 rovers also carried retroreflectors, adding to the network. The Lunokhod 1 reflector was lost for decades. Scientists knew roughly where it was, but could not get a return signal, possibly because the rover had parked in a position that angled the reflector away from Earth. In 2010, the Lunar Reconnaissance Orbiter photographed the Lunokhod 1 rover from orbit, pinpointing its exact location, and shortly afterward, the Apache Point Observatory successfully bounced a laser off its reflector for the first time in nearly 40 years. For over half a century, scientists have been pinging these reflectors with lasers, accumulating the most precise record of the Moon's orbit ever assembled. The data is unambiguous. The Moon is spiraling outward at 3.8 centimeters per year, but the data has also yielded far more than just the recession rate. Lunar laser ranging has confirmed Einstein's theory of general relativity to extraordinary precision, verified that the Moon and the Earth fall toward the Sun at the same rate, a test of the equivalence principle, and measured the tiny wobbles in the Moon's orbit caused by its internal structure, helping to confirm the existence of the partially molten layer around its core. Why is this happening? The answer is tidal friction. The Moon's gravity raises tidal bulges on Earth, not just in the oceans, but in the solid rock of the Earth's crust and mantle as well. Because the Earth rotates faster than the Moon orbits. Earth completes a rotation in 24 hours, while the Moon takes about 27 days to orbit. The tidal bulges are carried slightly ahead of the Moon's position by Earth's rotation. This creates a gravitational asymmetry. The near side tidal bulge, which is slightly ahead of the Moon, pulls the Moon forward in its orbit, giving it a tiny boost of energy. The extra energy causes the Moon to move to a slightly higher orbit, further from Earth. At the same time, the Moon's gravity pulls back on the tidal bulge, slowing Earth's rotation. The energy is transferred from Earth's rotation to the Moon's orbit. Earth spins slower. The Moon moves farther away. The consequences are measurable. Earth's day is getting longer, by about 2.3 milliseconds per century. That does not sound like much, but over hundreds of millions of years, it adds up dramatically. During the age of the dinosaurs, about 70 million years ago, a day on Earth was only about 23.5 hours long. Go back further, to about 1.4 billion years ago, and geological evidence suggests that a day was only about 18 hours long, and the Moon was significantly closer to Earth than it is today. Run the clock backward, and the implications are dramatic. If the Moon is moving away at 3.8 centimeters per year now, and if the rate was faster in the past, when the Moon was closer and the tidal forces were stronger, then the Moon was once very close to the Earth. Shortly after its formation, the Moon may have been only about 20,000 kilometers away, compared to its current distance of about 384,000 kilometers. At that distance, the Moon would have appeared enormous in the sky, perhaps 20 times larger than it appears today, dominating the heavens, raising tides hundreds of meters high on the young Earth, with an orbital period of only a few hours. The early Earth-Moon system was a wildly different place, almost unrecognizable compared to the world we inhabit today. Earth spun much faster. A day may have been only about 6 hours long. The sun rose, crossed the sky, and set again before you could finish what we would now call a morning. The Moon loomed overhead, vast and close, perhaps 20 times larger in the sky than it appears today. A colossal presence dominating the heavens, visible even in daylight, its surface features clear to the naked eye. Imagine standing on the young Earth and looking up to see a Moon that filled a significant fraction of the sky. Its craters, its mountains, its dark maria visible in extraordinary detail. Hanging so close, it seemed you could reach out and touch it. The tidal forces from this nearby Moon were immense, perhaps 1,000 times stronger than today's tides. The oceans, still forming and growing from outgassing volcanoes and incoming comets, were pulled into enormous tidal bulges that swept around the planet every few hours. These were not the gentle 2-meter tides we see on today's coastlines. They were walls of water tens of meters high, perhaps hundreds of meters in some configurations, surging across the young ocean basins with tremendous energy, scouring the shorelines, churning the seabed, mixing the chemistry of the early ocean with a violence that has no modern analog. Even the solid rock of Earth's surface flexed under the tidal stress, the crust rising and falling by meters with each cycle, generating enormous amounts of frictional heat that added to the internal warmth of the young planet. Over billions of years, tidal friction gradually transferred energy from Earth's rotation to the Moon's orbit, slowing the Earth and pushing the Moon outward, in a process that continues to this day. The system has evolved from a tightly coupled, rapidly spinning pair, 6-hour days, a nearby Moon, enormous tides, to the configuration we see today, a 24-hour day, a moon 384,000 kilometers away, receding slowly into the distance. It is one of the most elegant examples of energy transfer in the solar system. A slow, patient exchange that has been running for 4.5 billion years and will continue for billions more. And this process has another consequence, one that defines how we see the moon and how the moon sees us. The moon always shows the same face to Earth. Always. Every time you have looked at the moon, every full moon you have ever seen, every crescent, every gibbous phase, you have been looking at the same hemisphere, the craters, the dark Maria, the pattern that some cultures see as a face, others as a rabbit, others as a woman carrying a bundle of sticks. It is always the same image, unchanging, fixed, as if the moon were a painting hung on the wall of the sky. This is not a coincidence. It is a direct result of tidal locking. The same tidal forces that are pushing the moon away have also synchronized the moon's rotation with its orbit. The moon rotates on its axis once every 27.3 days, exactly the same period as its orbit around the Earth. The result is that the same hemisphere always faces Earth, and the opposite hemisphere, the far side, is perpetually turned away. Tidal locking happened early in the moon's history, when it was much closer to Earth and the tidal forces were much stronger. The tidal bulge, raised on the moon by Earth's gravity, acted as a brake on the moon's rotation, gradually slowing it until the rotation period matched the orbital period. Once locked, the configuration is stable. Any perturbation is corrected by the tidal forces, keeping the same face pointed toward Earth. But the lock is not perfect. The moon's orbit is slightly elliptical, which means it moves faster when it is closer to Earth and slower when it is farther away. But its rotation rate is constant. This mismatch causes the moon to appear to wobble slightly, a phenomenon called libration, revealing a thin strip of the far side around the edges. Thanks to libration, we can actually see about 59% of the moon's surface from Earth over time, rather than exactly 50%. The far side of the moon remained completely unknown until October 7, 1959, when the Soviet spacecraft Luna 3 flew behind the moon and photographed the far side for the first time. It was one of the boldest missions of the early space age, a spacecraft launched just 2 years after Sputnik, carrying a camera that used actual film, which was developed automatically on board the spacecraft, scanned by a television system, and transmitted back to Earth as a grainy, barely legible image. The technology was primitive by today's standards. The images were blurry, noisy, and covered only a portion of the far side, but they were enough to reveal a stunning surprise. The far side looked completely different from the near side. It was almost entirely covered in bright, ancient highlands, the heavily cratered terrain of the original crust. There were almost no Maria, none of the dark, smooth volcanic plains that dominate the near side. The moon's two faces were dramatically, unexpectedly different. The reason for this dichotomy remains one of the great unsolved problems in lunar science. The most widely accepted explanation involves the asymmetric distribution of heat-producing radioactive elements. A layer of material enriched in elements like thorium and uranium, which produce heat through radioactive decay, is concentrated on the near side, perhaps as a result of the asymmetric solidification of the magma ocean or the dynamics of the giant impact itself. This excess heat thinned the near-side crust and enabled volcanic eruptions that flooded the large impact basins with basalt lava, creating the dark Maria. The far side, lacking this heat source, remained geologically quieter, its crust thicker, its volcanism limited, its ancient surface largely preserved. China's Chang'e 6 mission in 2024, which collected and returned the first samples from the moon's far side, from the South Pole Itken Basin, has begun to test these ideas directly. The analysis of the far side samples revealed two periods of volcanic activity approximately 4.2 billion and 2.8 billion years ago, lasting at least 1.4 billion years. The far side was not completely dead. It had volcanism, but less extensive and from a different type of mantle source than the near side. The far side basalts come from an extremely depleted source, a mantle that had been stripped of many of its easily melted components, possibly by the enormous South Pole Itken impact itself, the largest confirmed impact basin in the solar system at roughly 2,500 kilometers across and 8 kilometers deep. The Chang'e sat analysis also revealed that the water content of the far side mantle is significantly lower than the near side mantle, evidence that the moon's interior is not uniform, and that the giant impact and the subsequent magma ocean created lasting chemical asymmetries that persist to this day. This is surprising discovery number 7. We are going back, and this time we are staying. For 50 years after the last Apollo mission in December 1972, no human being set foot on the moon. No human even left low Earth orbit. The Apollo program, one of the greatest achievements in the history of exploration, ended not with a permanent presence, but with a retreat. The flags and footprints and retro-reflectors remained, but the astronauts came home, and no one followed. To understand the magnitude of what Apollo achieved and why it ended, we need to remember what it was. Between July 1969 and December 1972, 12 human beings walked on the surface of the moon. 12. In all of human history, only 12 people have stood on another world. They collected 382 kilograms of lunar samples, rocks, soil, core tubes, and brought them back to Earth. Those samples have been analyzed continuously for over 50 years, and they are still yielding new discoveries. The astronauts deployed seismometers, laser retroreflectors, solar wind collectors, magnetometers, and heat flow probes. They drove a battery-powered rover across the lunar surface at speeds of up to 13 kilometers per hour, exploring valleys and mountains and craters that no human eye had ever seen. Apollo 11 landed in the Sea of Tranquility, a flat, safe, conservative choice for the first landing. Apollo 12 landed with pinpoint precision in the Ocean of Storms, just a few hundred meters from the Surveyor 3 probe that had landed 2.5 years earlier. Apollo 14 explored the Fra Mauro Highlands. Apollo 15 landed at Hadley Riley, a sinuous channel carved by ancient lava flows at the base of the Apennine Mountains. Apollo 16 explored the Descartes Highlands, the only mission to land in the ancient highland terrain. And Apollo 17, the last mission, in December 1972, landed in the Taurus Littrow Valley, a deep, narrow valley at the edge of the Sea of Serenity, where astronaut and geologist Harrison Schmitt discovered orange soil. Tiny beads of volcanic glass erupted from deep within the moon billions of years ago, containing trace amounts of water and other volatiles that hinted at the wet interior that would not be confirmed for another 4 decades. The reasons Apollo ended were complex, political, financial, technological. The Apollo program was driven by Cold War competition, not by a sustained commitment to exploration. Once the political goal was achieved, proving American technological superiority by landing humans on the moon before the Soviet Union, the motivation evaporated. The budgets were cut. Apollo 18, 19, and 20 were cancelled. The Saturn V rocket, the most powerful rocket ever built at that time, was retired without a successor. The astronauts returned to Earth orbit, and the moon became, once again, a distant light in the sky. But the story did not end there. Over the decades that followed, robotic missions continued to explore the moon, orbiters mapping its surface in exquisite detail, measuring its gravitational field, detecting water ice at the poles, and revealing the complex geology hidden beneath the regolith. NASA's Lunar Reconnaissance Orbiter, launched in 2009, has been orbiting the moon for over 17 years, mapping the surface at a resolution of 50 centimeters per pixel, sharp enough to see the Apollo landing sites, the rover tracks, even the trails of astronaut footprints in the regolith. The LRO has photographed every square kilometer of the moon multiple times under different lighting conditions, creating the most detailed map of any world beyond Earth. Its laser altimeter has measured the topography of the entire moon with a vertical accuracy of about 10 centimeters, revealing the subtle slopes and ridges that define the boundaries of ancient impact basins, the walls of permanently shadowed craters, and the gentle swells of volcanic domes. Japan's Kaguya orbiter, launched in 2007, mapped the moon's gravity field and detected gravity anomalies, mass concentrations, or mascons, hidden beneath the large impact basins, the dense plugs of mantle material that welled up after the impacts and froze in place, creating gravitational bumps that subtly alter the orbits of spacecraft passing overhead. India's Chandrayaan missions pushed the boundaries of lunar exploration, detecting water and landing near the South Pole. China's Chang'e program, methodical, ambitious, and relentlessly successful, progressed from orbit to landing, to roving, to sample return, with a precision and pace that has made it the dominant force in robotic lunar exploration in the 21st century. Each mission added new layers to our understanding, building the case for a return. And the return is now underway. NASA's Artemis program is the agency's plan to return humans to the moon. And this time, the goal is not a brief visit, but a sustained presence. The program is built around the Space Launch System, or SLS, the most powerful rocket ever built, capable of sending the Orion spacecraft and its crew beyond low Earth orbit to the moon. Artemis 1, launched in November 2022, was an uncrewed test flight that sent an Orion capsule around the moon and back, demonstrating the systems needed for crewed missions. Artemis 2, the first crewed mission, is scheduled to launch in 2026, carrying 4 astronauts on a flight around the moon and back, the first time humans have traveled beyond low Earth orbit since Apollo 17 in 1972. The mission experienced delays due to the need for further analysis of the Orion heat shield, which performed differently than expected during Artemis 1. But the issues have been resolved and the mission is on track. The ambitions grow from there. Later Artemis missions plan to land astronauts on the lunar surface near the South Pole, the region where water ice has been detected in permanently shadowed craters. The landing will use new human landing systems developed by commercial partners, SpaceX Starship and Blue Origin's Blue Moon, representing a fundamentally different approach from Apollo, where NASA designed, built, and operated everything in-house. The Artemis architecture relies on commercial partnerships, sharing costs and risks with private companies in a way that would have been unimaginable during the Apollo era. The ultimate goal is a permanent lunar outpost, a base camp at the South Pole where astronauts can live and work for weeks or months at a time, conducting science, testing technologies for future Mars missions, and learning how to sustain human life on another world. The base would be located near the rim of a South Pole crater, ideally at a location that offers both access to permanently shadowed regions where water ice can be mined and access to nearby peaks of eternal light, elevated ridges where the sun is almost always visible, providing continuous solar power. The combination of water in the shadows and sunlight on the peaks makes the lunar South Pole uniquely suitable for a permanent base, a place where the two most critical resources for long-term habitation are available within walking distance of each other. The Gateway, a small space station in lunar orbit, will serve as a staging point, allowing crews to transfer between the Orion spacecraft and the lunar lander without needing to bring everything down to the surface and back up again. The Gateway will orbit the Moon in a near rectilinear halo orbit, an elongated, energy-efficient orbit that brings the station close to the Moon at its lowest point and far from the Moon at its highest, providing coverage of the lunar South Pole and convenient access for arriving and departing spacecraft. The first modules of the Gateway are expected to launch in the late 2020s, with the station gradually growing as new modules are added. The vision extends beyond the base itself. Future missions plan to deploy rovers that can enter permanently shadowed craters, drill into the regolith, extract water ice, and transport it back to the base for processing. Prototype systems for extracting oxygen from lunar soil, a process called molten oxide electrolysis, have been tested in laboratories on Earth and could eventually provide breathable air from the Moon's own rocks. Three-dimensional printing technologies are being developed that could use lunar regolith as a building material, constructing habitats, landing pads, and radiation shields from local materials rather than importing everything from Earth. The goal is not just to visit the Moon, but to live off the land, to create a self-sustaining infrastructure that reduces the dependence on Earth and makes the Moon a practical launching point for deeper exploration. But NASA is not alone. The Moon has become a destination for the world, a convergence of ambition, technology, and national prestige unlike anything since the original space race. China's lunar program, arguably the most successful robotic exploration program of the 21st century, has achieved a series of remarkable firsts with a methodical persistence that has reshaped the landscape of space exploration. Chang'e 3 landed a rover on the near side in December 2013, making China only the third country to achieve a soft landing on the Moon after the Soviet Union and the United States. The U-2 rover, named after the jade rabbit of Chinese mythology, explored the surface for months, analyzing basalt rocks in the northern Mare Imbrium with its ground-penetrating radar and spectrometers. Chang'e 3 became the first spacecraft to land on the far side of the Moon in January 2019. An achievement that required solving a problem no space agency had ever faced before. Because the far side of the Moon never faces Earth, there is no direct line of sight for radio communications. Any spacecraft on the far side is cut off from ground control, unable to send data, unable to receive commands, essentially invisible. To solve this, China launched the Ke-Chao relay satellite in May 2018, placing it in a halo orbit around the second Earth-Moon Lagrange point, a gravitationally stable position about 65,000 kilometers beyond the Moon, where the satellite has a continuous line of sight to both the far side and the Earth. Ke-Chao, named after the bridge of magpies from Chinese mythology, serves as a communication bridge, relaying signals between the Chang'e 4 lander and mission control in Beijing. It was an elegant solution to a fundamental problem, and it worked flawlessly. Chang'e 4 landed in Von Karman crater, a 180-kilometer wide impact crater within the enormous South Pole Aitken Basin, and deployed the Yutu-2 rover, which has now traveled more than 1.5 kilometers across the far side surface, studying the composition of rocks and soil that no human or robot had ever touched. Chang'e batch returned samples from the near side in December 2020. 1,731 grams of lunar material scooped and drilled from a young volcanic region in Oceanus Procellarum, the first lunar sample return since the Soviet Luna 24 mission in 1976. The samples revealed that volcanism on the Moon continued until as recently as 2 billion years ago, far more recently than most models had predicted, and that the late-stage volcanic rocks had unexpectedly low water content, challenging assumptions about the Moon's interior. On Chang'e alv, in 214, returned samples from the far side, 1,935 grams, from the South Pole Aitken Basin, completing a mission that required the upgraded Quechua-2 relay satellite and pushed the boundaries of autonomous robotic operations on another world. India's Chandrayaan-3 achieved a historic soft landing near the lunar South Pole in August 2023, making India the fourth country to land on the Moon and the first to land near the South Pole. The Vikram lander and Pragyan rover operated for about 2 weeks before the long lunar night ended their mission. But in that time, they confirmed the presence of sulfur, iron, calcium, and other elements in the polar soil. Data that will inform future landing site selections and resource utilization plans. Japan's Slim lander, the smart lander for investigating Moon, touched down in January 2024, making Japan the fifth country to achieve a soft lunar landing. Slim demonstrated precision landing technology, touching down within 100 meters of its target, a feat that earned it the nickname Moon Sniper. Though it landed at an unexpected angle that limited its solar power, the mission successfully deployed 2 small rovers and demonstrated technologies that will be crucial for future missions targeting specific geological features. The Moon is experiencing a second space race, but this time it is not just 2 superpowers competing for prestige. It is a global effort, with multiple nations and private companies all converging on the same destination, driven by a combination of scientific curiosity, geopolitical competition, commercial interest, and the practical recognition that the Moon's resources, particularly its water ice, could be the key to opening the solar system to sustained human exploration. The footprints that Neil Armstrong left in the Sea of Tranquility in July 1969 are still there. Without wind, without rain, without any of the erosional forces that would erase them on Earth, the footprints will persist for millions of years, perhaps tens of millions, disturbed only by the slow rain of micrometeorites that gradually churn the uppermost layer of regolith at a rate of about 1 millimeter per million years. The bootprints are sharp and crisp, pressed into the fine-grained regolith with the clarity of footprints in wet cement. The rover tracks from Apollo 15, 16, and 17 are still there, parallel lines in the dust stretching across the lunar surface. The descent stages of the lunar modules are still there, squat, gold foil-wrapped platforms sitting on their landing legs exactly where they touched down. The flags are still there, though the fabric has almost certainly been bleached white by decades of unfiltered ultraviolet radiation. The scientific instruments, the discarded tools, the commemorative plaques, the 2 golf balls that Alan Shepard hit during Apollo 14, all of it is still there, undisturbed, a museum of human achievement on an airless, timeless world. They are the oldest human artifacts on another world, and they may be there long after every trace of our civilization on Earth has disappeared. But they will not be the last. The next footprints on the moon will be made near the South Pole, in the shadows of craters that hide water ice, within reach of resources that could sustain a human presence not for hours or days but for years. The moon is not just a destination, it is a stepping stone, the first stop on a journey that may eventually take us to Mars, to the asteroids, and beyond. Let us step back now and consider the moon as a whole. This small, battered, ancient world that has been our companion for 4.5 billion years. The moon is small. Its diameter is about 3,474 kilometers, roughly the width of the continental United States. Its mass is only about 1.2% of Earth's mass. Its surface gravity is about 1/6 of Earth's. An astronaut who weighs 80 kilograms on Earth weighs only about 13 kilograms on the moon. You could jump 6 times higher on the moon than on Earth. You could throw a ball 6 times farther. But the moon's influence on Earth is enormously out of proportion to its size. The moon stabilizes Earth's axial tilt, the 23.5-degree lean that gives us seasons. Without the moon, Earth's tilt would vary chaotically over millions of years, driven by the gravitational tugs of Jupiter and the other planets, swinging from nearly 0 degrees to perhaps 45 degrees or more. The result would be extreme, unpredictable climate shifts, periods when there are no seasons at all, followed by periods when the poles bake in summer sunlight and the equator freezes in winter. The moon acts as a gravitational anchor, keeping Earth's tilt relatively stable, ensuring that the seasons change gradually and predictably over thousands of years rather than wildly over millions. The moon also drives the tides, the rhythmic rise and fall of the oceans that has shaped the evolution of life on Earth. Tides create the intertidal zone, the strip of shoreline between high tide and low tide, which is one of the most biologically productive environments on the planet, a zone of constant change where marine organisms are alternately submerged and exposed, creating evolutionary pressure that may have played a crucial role in the transition from sea life to land life hundreds of millions of years ago. Without the moon, Earth's tides would be driven solely by the sun and would be only about 1/3 as strong. The intertidal zone would be narrower, the tidal mixing of nutrients less vigorous, and the evolutionary pathway from ocean to land potentially very different. Some scientists have even speculated that the moon was essential for the origin of life itself, that the strong tides of the early Earth, driven by a much closer moon, created shallow tidal pools where organic molecules could concentrate, interact, and eventually give rise to the first living cells. The mechanism is elegant. As tidal waters flood the shore and then retreat, they leave behind pools of water enriched in dissolved minerals and organic molecules. The pools evaporate in the sunlight, concentrating the molecules further. Then the next tide arrives, diluting the mixture, mixing it, redistributing it across the shore. This cyclical process of concentration and dilution, repeated billions of times over millions of years, could have driven the chemical reactions that eventually crossed the threshold from complex chemistry to simple biology. The idea is speculative and hotly debated, but it is not unreasonable. The moon has been shaping Earth's environment since the moment of its birth, and the possibility that it also shaped the conditions for life is a tantalizing thought. There is another subtle but important influence that the moon exerts on Earth. It slows the winds. Tidal friction does not just affect the oceans, it creates atmospheric tides as well, subtle oscillations in air pressure driven by the moon's gravity. These atmospheric tides are tiny compared to the ocean tides, but they are measurable, and they contribute to the overall energy dissipation that gradually slows Earth's rotation. A slower rotation means weaker Coriolis forces, which in turn means weaker jet streams and, in theory, slightly calmer weather patterns. Without the moon, Earth would rotate faster, the winds would be stronger, and the weather would be more extreme. Climate models suggest that a moonless Earth might have sustained surface winds averaging 60 to 100 kilometers per hour, a permanently windswept world, far less hospitable than the one we know. The moon has also served as Earth's shield, absorbing impacts from asteroids and comets that might otherwise have struck our planet. The moon's surface is covered with craters, tens of thousands of them, ranging from microscopic pits to enormous basins hundreds of kilometers across. The largest, the South Pole Aitken Basin on the far side, is roughly 2,500 kilometers in diameter and 8 kilometers deep, one of the largest confirmed impact structures in the solar system. Every one of those craters represents an impact that did not hit Earth. The moon has been absorbing blows for 4.5 billion years, and while some of those impactors would have missed Earth anyway, the moon's gravitational influence has deflected others, serving as a partial shield for the inner solar system. The moon is a time capsule, perhaps the most important archive in the solar system. Because it has no atmosphere, no water, no plate tectonics, none of the geological processes that constantly resurface and reshape the Earth, its surface preserves a record of events that has been erased on our own planet. The ancient highlands, the impact basins, the lava flows, the regolith, all of it is a record of the solar system's history, written in rock and preserved in vacuum, waiting to be read. Consider what we have lost on Earth. Our planet is geologically alive. Its surface is constantly being recycled by the engine of plate tectonics. Oceanic crust is created at mid-ocean ridges, pushed across the ocean floor over millions of years, and then subducted back into the mantle at convergent boundaries, where it is melted, reformed, and eventually returned to the surface as new rock. The oldest oceanic crust on Earth is only about 200 million years old, less than 5% of the planet's history. Continental crust is older, but it too is constantly being eroded, folded, metamorphosed, and recycled. The oldest rocks on Earth, the Akasta gneiss in northern Canada, are about 4 billion years old, but they represent tiny scattered fragments of the early Earth, heavily altered by heat and pressure, their original character almost completely overwritten. The first 500 million years of Earth's history, the period called the Hadean. After Hades, the Greek underworld, is almost entirely missing from the geological record. The rocks from that era have been recycled, subducted, melted, and reformed so many times that almost nothing remains. We know that the Earth was bombarded by asteroids and comets during this period. We know that the surface was hot, possibly molten. We know that water appeared at some point, perhaps delivered by comets, perhaps outgassed from volcanic eruptions, but the details, the timing, the intensity, the sequence of events are almost entirely lost. The moon preserves what Earth has erased. Its surface is a frozen record of the solar system's violent youth, undisturbed by the geological recycling that has destroyed the equivalent record on our planet. The ancient highlands, the bright, heavily cratered terrain that covers most of the far side and much of the near side, date back to the moon's earliest history, 4.3 to 4.4 billion years old. Every crater is a timestamp, a record of an impact that happened at a specific time with a specific energy, from a specific direction. By counting craters and measuring their sizes, scientists can estimate the rate of bombardment over time, building a chronology of impacts that tells the story of the inner solar system's evolution. The most dramatic chapter in that story is the late heavy bombardment, a cataclysmic period roughly 4 billion to 3.8 billion years ago, when the rate of impacts in the inner solar system spiked dramatically. The evidence is written across the moon's face in the form of enormous multi-ring impact basins: Imbrium, Orientale, Serenitatis, Nectaris, Crisium. Each one hundreds of kilometers across, each one the scar of a collision with an asteroid tens of kilometers in diameter. These basins are clustered in age. They all formed within a relatively narrow window of time, suggesting that something happened in the solar system roughly 4 billion years ago that sent a barrage of large asteroids cascading into the inner solar system. The leading explanation, known as the Nice model, after the city in France where it was developed, proposes that the late heavy bombardment was triggered by a gravitational resonance between Jupiter and Saturn. As the two giant planets migrated through the outer solar system in the first billion years after the Sun's formation, they crossed a critical orbital resonance, a point where their orbital periods locked into a simple ratio that destabilized the orbits of millions of smaller bodies in the outer solar system. Asteroids and comets that had been orbiting peacefully for hundreds of millions of years were flung into chaotic trajectories, many of them plunging inward toward the inner solar system. The Moon, Earth, Mars, Mercury, and Venus were all bombarded simultaneously, but only the Moon has preserved the evidence in its craters. The Nice model has been debated and refined since it was first proposed in 2005. Some scientists argue that the late heavy bombardment was not a single spike, but a gradually declining tail of impacts from the era of planet formation. Others have proposed that the migration of the giant planets happened earlier than the Nice model suggests, and that the bombardment was spread over a longer period. The debate continues, but the craters on the Moon provide the raw data, the timestamps, the sizes, the frequencies that any model must explain. On Earth, the rocks from that era have been recycled by plate tectonics, subducted into the mantle, melted, and reformed. The record is fragmentary and incomplete, but on the Moon, the record is intact, preserved for 4.5 billion years, waiting for us to read it. The Apollo samples, the Luna samples, the Chang'e samples, each one is a page from a book that Earth lost long ago, a book that tells the story of the solar system's youth. Every grain of lunar soil contains a history, implanted solar wind particles recording the sun's activity over billions of years, cosmic ray tracks recording the flux of high-energy particles from distant supernovae, micrometeorite impacts recording the rain of interplanetary dust. The Moon is not just a time capsule of its own history. It is a time capsule of the solar system's history, an archive that Earth desperately needs and cannot provide on its own. The Moon is also, in a very real sense, a mirror. When you look at the full moon on a clear night, you are seeing sunlight reflected off a surface that has been bombarded, baked, frozen, cracked, and pulverized for 4.5 billion years, but that still shines, still reflects, still sends light back to us across 384,000 kilometers of empty space. The light that reaches your eyes left the sun about 8 minutes ago, traveled to the moon in about 1.3 seconds, bounced off the ancient regolith, and traveled back to Earth in another 1.3 seconds. The moonlight you see is second-hand sunlight, sunlight that has touched another world before reaching you. And there is something deeply poetic about that. The moon does not generate its own light. It has no fire, no fusion, no internal luminosity. It shines only because it reflects the light of another, borrowing brightness from the sun, returning it to us softened and silvered, transformed from the harsh glare of a nuclear furnace into the gentle glow that has inspired poets and lovers and dreamers for as long as humans have looked up at the sky. Tonight, the moon is out there, close and familiar and full of surprises. A world born in a collision that melted the earth, forged in a magma ocean that took 200 million years to cool, shaken by quakes that ring through its dry, rigid crust for 10 minutes at a time, once shielded by a magnetic field that flickered and died, hiding vast reserves of water ice in shadows that have not seen sunlight for billions of years, slowly drifting away from us at the pace of growing fingernails, locked in a gravitational embrace that stabilizes our seasons and drives our tides. It is the only world beyond Earth where a human being has stood. The footprints are still there, sharp and clear in the fine gray dust, undisturbed by wind or rain, waiting in the silence for the next visitors to arrive. And they are coming. Not for a brief visit this time, but to stay, to build, to learn, to use the water in the shadows and the sunlight on the peaks to create something lasting. A human presence on another world, a stepping stone to the planets, a beginning. The moon is not the end of the story. It is not even the middle. It is the prologue, the first chapter in a story that humanity is only now beginning to write. And the next chapter starts at the South Pole, in the eternal shadows, where the water is waiting. The moon has been many things to humanity over the millennia. To the ancient Sumerians, it was Nanna, the father of the gods, who measured time by his waxing and waning. To the Greeks, it was Selene, riding her silver chariot across the night sky. To the Chinese, it was home to Chang'e, the goddess who drank the elixir of immortality and floated upward to live among the jade palaces of the lunar surface. To the Islamic world, the crescent moon became a symbol of faith, adorning the domes of mosques from Istanbul to Jakarta. To the navigators of Polynesia, the same culture that gave us the word Laniakia, meaning immeasurable heaven, the moon was a guide, its phases and position marking the passage of time and the changing of seasons on voyages across thousands of kilometers of open ocean. Every culture that has ever looked up at the night sky has seen the moon and tried to understand it, to name it, to worship it, to tell stories about it, to fit it into a framework of meaning that made sense of the world. The moon was a clock before we had clocks, a calendar before we had calendars, a light in the darkness before we learned to make fire. The English word month comes from the same root as moon. The English word Monday means moon's day. Our most basic units of time, the month, the week, even the concept of a regular cyclical calendars, are echoes of the moon's orbit, artifacts of a time when the phases of the moon were the most reliable clock available to any human being on Earth. And now we are going back to the moon with instruments and ambitions that those ancient stargazers could never have imagined. We are going back not to plant a flag and leave, we did that 50 years ago, but to build, to stay, to learn, and eventually to use the moon as a launching pad for the rest of the solar system. The water ice hiding in the permanently shadowed craters of the South Pole may become the fuel that carries humanity to Mars. The regolith that plagued the Apollo astronauts may become the building material for the first structures on another world. The helium-3 embedded in the lunar soil by billions of years of solar wind bombardment may one day fuel fusion reactors that power cities on Earth, or none of that may happen. The future is uncertain. Programs are delayed, budgets are cut, priorities shift. The history of space exploration is littered with cancelled missions, abandoned plans, and grand visions that never materialized. But the moon is patient. It has been waiting for 4.5 billion years. It can wait a little longer. Close your eyes. Let the moonlight in. It has traveled a long way to reach you. From the sun to the moon and back again. Second-hand light from an ancient world, a world that was born in fire, grew in silence, and is waiting, patient and quiet, for us to return. Think about what we have learned tonight. A world born in the most violent collision in Earth's history, assembled from the wreckage of 2 shattered planets. A magma ocean that glowed in the darkness for 200 million years. A crust that still shakes with quakes that ring for 10 minutes. A magnetic field that flickered to life, shielded the surface for billions of years, and then died. Water ice hiding in shadows where sunlight has never reached. A slow, patient retreat, 3.8 centimeters per year, measured by laser beams bouncing off reflectors that astronauts placed there more than 50 years ago. And a world that, despite being our closest neighbor, despite being the only place beyond Earth where human footprints exist, still holds secrets we have barely begun to uncover. The moon is not what you thought it was. It is stranger, older, more complex, and more important than you ever imagined. And it is right there, closer than any other world, brighter than any other light in the night sky, as familiar as the face of an old friend. An old friend with secrets it has kept for 4.5 billion years. The night is quiet. The moon is bright. Let yourself drift